Good morning. All right, we'll get started. We're continuing with Newton's laws, so problems involving F equals ma, and that includes circular motion and centripetal force. So we'll continue with those today. First, I want to talk a little bit about apparent weight. So, of course, we know the difference between mass and weight. Mass is how much stuff something is made of. So that never changes. If you measure the mass of an object on Earth, it's the same as if you measure the mass of that object on the moon or just floating out in space, right? Mass never changes. It's how much stuff something is made of. Weight is a gravitational interaction with some object, like the Earth or a moon or another planet. So that can change because you're going to interact differently with the Earth that you will with the moon or with Mars, or if you're just floating out in space, not interacting with anything. How much stuff something is made of. And this is always the same. Okay, no matter where you are in space, mass is mass, does not change. Weight is a force, and it's a gravitational force between an object and a planet or moon. And that can change, right? Obviously, you're going to have a different, if you weigh something on the Earth, then you weigh it on the moon, it weighs much less on the moon because the moon is not as massive. Okay, so let's talk about, we've got a person standing on a scale. There's our person. And let's draw a Freebody diagram for them. What's touching our person? The scale, right? That can interact through a normal force and through friction, but the person's just standing there on level ground, so there's no friction force. And what can reach in from a distance? Force of gravity, which is mg. And if that person is just standing there, we know the normal force equals the weight. So the scale is reading the actual weight of the person, m times g. So let's put some numbers in here. And I'm just going to use g is equal to 10. So I can do this in my head. All right, so we're going to take our person and our scale, and we're going to put them in an elevator. Here's my person and my scale and my elevator. Okay. We'll go through a whole bunch of different scenarios here. We're going to start with the simplest one. The elevator is at rest. Okay. So tell me what the scale reads. Okay. So when I say the sum of the forces is going to be 0 on our person, I've already drawn my free body diagram. I have normal force minus mg is 0, or normal force equals m times g, which I said was going to be 50 and 10. So 500 newtons. All right, so let's make it a little more interesting. Now the elevator starts to go down. Oops. And so it's accelerating in that direction. What does the scale read? What does the person feel? The scale is telling us the weight that the person feels. Does the person feel heavier or lighter? Person feels lighter because the floor is dropping out from underneath them, right? They're not pressing into the floor as hard. It's as if we reduced gravity magically, right? So the person feels lighter, and we call that their apparent weight. So the apparent weight is how much the person is interacting with the surface they're on. And the normal force here from our scale is reading, the scale reads the apparent weight, right, which is the normal force. So what do they weigh here? Sum of the forces equals ma. I'll say up is positive. So I have a normal force in the positive direction, force of gravity in the negative direction, m times the acceleration. And what's the acceleration? It's 2 meters per second squared, but in what direction? The negative direction. So my normal force is mg minus 2m. Oops, 400 newtons. Has to be lighter. 400 newtons. So the person feels lighter. Their apparent weight is 400 newtons. That's how they are interacting with the floor they're standing on. The floor is pushing back with the force of 400 newtons. That's how heavy they feel. They feel lighter at that instant because of the acceleration. Now what happens? The elevator started to go down. That's what we just did. Now it hits its traveling speed, right? And so it just travels at constant speed as it continues down, down, down the building shaft there, the elevator shaft. So let's see what happens then. So this is going to be moving at constant speed. And it's going down. Okay, what's the scale read now? What's the apparent weight of our person in the elevator? Okay, back to normal, because we don't care about the velocity. What do we care about? acceleration. And here the acceleration is 0, same as if they were standing still, right, in the still elevator. And so we get sum of the forces equals 0. Normal force equals mg, 500 newtons. Now what's going to happen? The elevator has to slow down now so it can come to a stop. So that means if the elevator is going down and it's slowing down, the acceleration has to be up. Does the person feel heavier or lighter now? Heavier, because they have inertia. They want to keep moving down at the same rate, but the floor is slowing down, stopping, and so their body is pressing harder into the floor. Yeah, it all depends on acceleration. It all depends on the acceleration. So sum of the forces equals ma. Up is my positive direction. So I've got n minus mg is m times plus 2 this time, right? And I plug in my numbers, and I've got my normal force is 600 newtons. Their apparent weight is 600 newtons. The apparent weight is what a scale would read if they were standing on it, or what a scale would read if they were sitting on it. It's the normal force between that person, that object, and the surface they're interacting with. Okay, let's do one more. Let's do this case. Oh no. What's the apparent weight of our person in this unfortunate situation? We say sum of the forces equals ma. Up is my positive direction. Normal force minus mg is m. And what is their acceleration now? Gravity, right? And I chose up as positive, so I have to put minus g here. And so I get my normal force is 0. The normal force is 0. And what do we call this? We call it weightlessness, right? That's the term we use, weightlessness. I'll write it here. So what is the person's weight, actual weight, as they're in that elevator falling? Has their mass changed? Has the force of gravity all of a sudden disappeared? No. Their mass is the same. Their mass is the same. It never changes. The force of gravity certainly didn't change, instantly turn off, right? Their weight is still the same, right? Their interaction with the earth is still the same. The earth was pulling on them with 500 newtons when the elevator was standing still, and it's still pulling on them with 500 newtons as the elevator's falling with an acceleration of g, right? So their actual weight has not changed. Their apparent weight has changed. They feel like they are weightless because there's nothing pushing back on them. There's no support force. So the term weightlessness is a little misleading, isn't it? We really shouldn't call it weightlessness. We should call it support forcelessness. That's what we should call it. Support forcelessness. So when the support force goes lower, or in this case to zero, the person feels lighter and or even weightless. When the support force increases, then the person feels heavier. So you can see where, let's take another look at our free body diagram for a second. Normally, right, normally the two forces are the same and the person doesn't accelerate. They don't move up or down if they're standing on a scale in their bathroom, right? But if you take that scale into the elevator and you want to accelerate upward, what has to happen? One of these forces has to be bigger than the other, or there's not going to be any acceleration. Is the force of gravity magically going to change? No, that's pretty much fixed, right? That's not going to change. So what has to happen? The normal force has to get bigger if you're going to accelerate upward. The elevator starts to move upward, your body resists that motion because it has inertia, and you get pressed into the floor of the elevator a little bit, and the normal force increases until it's big enough to make you accelerate with the elevator. And the same thing happens when you're going down, when you're accelerating in the downward direction. One of these forces has to change, right? Is the force of gravity going to change? No way. So your normal force has to change. As the elevator floor starts to drop out underneath you, your body has inertia, resists that change in motion a little bit, and the floor starts to go out from underneath you, and the normal force becomes less. And when the normal force is just right compared to your weight to cause you to accelerate with the elevator, then it stops changing and it maintains that value. So the normal force here is what's changing. Yes, the question is, if the elevator is going down and slowing down, so that means the acceleration is upward at 2 meters per second, your apparent weight is the same as if the elevator was accelerating upward, moving upward and accelerating upward at 2 meters per second, because we don't care about the velocity. All we care about is acceleration. Yeah, I picked up as my positive direction because I thought that's what you would have done. But it doesn't matter. You can pick down as positive. The result is the same every time. You would have gotten, I guess if you chose down as positive, all your normal forces would be negative because they point upward. Okay, normal force. and apparent weight. So oftentimes we feel apparent weight. We'll talk a little bit more about it when you're going over a bump, like in the road. So in the elevator, certainly we feel it. We all know that feeling we get kind of in our stomach as the elevator goes up or down, and we kind of feel heavier or lighter, and you kind of feel it in your stomach. And going over a bump in the road or a dip in the road, same thing, right? Going over the top of the bump in the road, your body kind of, the car and the body want to keep going up as you go up that hill and over, and then so you feel lighter as you're going over the top of that hill, and when you go down through a valley, you feel heavier in that dip in the road. Apparent weight. Okay, let's take a look at let's take a look at a car going over a bump in the road. Let's do that. Car going over a speed bump. Mine is more like a speed hill, but that's okay. Okay, so if we are given, yes, yeah, you feel it in your stomach, yeah. We're given the mass of the car, radius of curvature of that circular path that the car is driving on. Find the maximum. Such that the car is just in contact with the ground. As it drives over that hill. All right, let's set this up. Go ahead. Circular motion problems, you should be thinking about centripetal force and Newton's laws. So free body diagram for that car, and apply the equation F equals ma to that. That's our velocity in this direction. Okay, what are we going to say? We're going to say the sum of the forces in the radial direction have to be m times a centripetal. And what direction are we going to choose as our positive direction? Towards the center of the circular path, right? Towards the center of the circle. This direction. So I'll choose radially inward, towards the center of the circle. In this case, it's down. Okay. What is the sum of the forces? We've got N minus mg. What is a centripetal? V squared over R. And let's think about this for a second. The weight can't change, right? The force of gravity is not going to magically change as the car drives over the hill. What can change is the normal force. So let's think about this for a second. If the car was not moving, if it was just parked there, V equals 0, what do we get? We get the normal force has to equal the weight, right? These two forces have to be equal. Oh, sorry. Oops. Is that better? Thank you for catching that. Just did all those elevator problems where my normal force was up and it was in my brain. Okay. That looks much better. Thank you. So let's make V 0. The car is parked there. V equals 0. That means the normal force and the weight are the same. Now let's drive over the hill real slowly. Just drive very slow, small v. So what just happened to my force of gravity? Nothing. It's the same as it was before. So what had to happen to n? It had to get a tiny bit smaller, right? In order to have this difference equal to some small number, right? If v is some small value, then the difference on the other side has to be some small value. So if I drive real slowly over the hill, my normal force gets a little bit smaller. Force of gravity stays the same. Now I drive a little bit faster over the hill. Well, the force of gravity didn't change, but what happens? The normal force has to get a little bit smaller to keep enough force difference in the radial direction to keep me moving in a circular path. So the normal force gets a little bit smaller. And I keep driving faster and faster and faster. And what happens? The normal force gets smaller and smaller and smaller until it goes to 0. And when the normal force goes to 0, the only force keeping me moving in a circular path as I go over that hill is the force of gravity. And if I try to go any faster than that, there's not enough force keeping me in a circular path, right? Because the road can't pull on me. It can only push on me with a normal force. So if I try to go faster than that, what's going to happen to the car? It's going to sail off the hill there. It's going to become airborne. We don't want that. It's going to spiral out, right? Remember, we talked last time about the force. Where was it? Yeah, this is from last time. And if the sum of the forces in the radial direction are not big enough to keep the object moving in a circular path, the object will spiral out. The radius will become larger. So our car going over the hill, that means its radius has to get bigger. It's going to fly off the hill there, become airborne. So the magic happens here when n goes to 0, we hit V maximum. Okay, so at V maximum, the maximum speed you can go and still be in a circular path, still be just in contact with the road, occurs when the normal force just goes to 0. And so what do we end up with here? We end up with V maximum is equal to the square root of RG. The mass cancels out. It doesn't matter what the mass is. We okay with that? We could use the same logic for something moving in a circle, like on a string, a vertical circle. Should we do that? Find the, in this case, the minimum speed needed to keep this moving in a circular path as it goes over the top of the circle. So we've got our, our object on a string, right, moving in a circular path. And when it gets to the top, we want to know what's the minimum speed we have such that that object continues to move in a circular path. Because if we try to go too slow, what's going to happen? It's going to fall off that path and spiral in, right? So you're drawing a Freebody diagram, applying Newton's second law. So in this case, we've got tension in the string and the force of gravity both towards the center of the circle, right? We say sum of the forces in the radial direction has to be m, times a centripetal tension minus plus mg m v squared over r. So in this case, we can think about it in the opposite direction, right? Because it takes speed to go to keep this thing moving in a circle. So let's think about what if v was really, really big? We had this thing whipping around really fast in a circle. Well, the force of gravity is nowhere near strong enough to keep it moving in a circular path. It would go flying off somewhere, right? So we have this string that applies a really big force, tension force, keeping it moving in a circle. Now we slow it down. We don't spin it quite as fast. The force of gravity does not change, so the tension must get a little bit smaller. We don't need as much force to keep our object moving in a circular path. Now we slow it down a little bit more. The force of gravity stays the same. The tension force gets a little bit smaller to keep it moving in a circular path. Now we slow it down a little bit more. And what can the tension do? It can go all the way. We can keep slowing it down until the tension force goes to 0. And gravity is providing the force needed to keep it moving in a circular path. But what happens if we try to slow it down any more than that? Gravity is not going to become less. It's going to stay the same. So our object is going to spiral in. It's going to, let's look at what we had last time. What did we have last time? It's going to be like this. The force of gravity is going to be too big to keep it moving in a circular path, and our object is going to spiral in. That means it's going to look like this. Where are we? It's going to fall off. It's not going to stay in a circular path, right? If the force of gravity is too big. So there's some magic value of V as we're making V smaller and smaller and smaller, where the tension just goes to 0 at that instant. And that's the minimum V we have to maintain circular path. If we try to go less than that, it falls off the circular path and spirals in. So at V minimum, the tension goes to 0. So we have mg is m And we get the square root of RG. Okay. So think about what can change and what can't, right? The force of gravity cannot change. That's a fixed value, but the tension in that rope can increase or decrease. The normal force can increase or decrease, okay? In fact, I have a video here. Where is it? Normal force. Let me share this with you. So students often have a hard time understanding that normal force reacts, right? It changes. If you're just standing on the floor, there's a certain normal force up on you, enough to hold you up. If you jump, you have to have a bigger upward force acting on you than gravity, right? The normal force has to be bigger than gravity. So when you try to jump up off the floor, your feet press down harder into the floor, and the floor presses back harder on you, and that causes you to go up, okay? So I wanted to really clearly illustrate that. I'm hoping this video does it. Oops, I didn't want to do that. Hold on. All right, before we watch this video, I want to assure you no drunk college students were hurt in the filming of this video, okay? Everyone's okay in the end. So here we go. We've got this guy standing on...
There you go.
Standing on a piece of wood, right? A handrail. And what's he gonna do? He's gonna jump. So right now, that wooden board he's standing on is providing a normal force equal to his weight. When he jumps, what does the normal force have to do? It has to increase, right? There has to be a bigger force up on him to get him to jump. Let's take a look.
Oh yeah!
Okay, that normal force has to increase. As he jumps, he's pushing down harder, and the normal force has to increase. Normally it does, right? Normally the floor doesn't break away, but in this case, it could not provide a big enough force, and it broke. Luckily, there was a nice soft landing there for him. Okay? All right, let's go back to... No, I don't want that. This is what I want. Okay. Let's do this one. So here we've got two boxes being pulled up an incline, tied together with a rope. They're going up a rough incline. That means there's friction there. A student considers the forces acting on this and says, I think the tension in the rope connecting the boxes has to be larger than the force the lower box exerts on that rope, because the tension is causing the lower block to accelerate up the incline. I think the tension in the rope connecting the boxes, so tension in that rope has to be larger than the force the lower box exerts on that rope, because tension is causing the lower block to accelerate up the incline. What do you think of this? So how about we let's walk through this one thing at a time. There's two ropes here, right? There's T1 and T2. Which one of those has to be bigger? T1, because T1 is accelerating 2m up the incline, but T2 is only accelerating m up the incline. So T1 has to be a lot bigger, right? Probably twice as big. I haven't thought about friction. Yeah, friction force is the same for both of them, right? So T1 would have to be twice as much. So now let's think about what they're saying here. What does T2 have to be greater? In order for M to accelerate up the incline, the last box here, T2 has to be greater than what forces? Should we draw a Freebody diagram for M? Yes. So what do we have? We have a normal force and a friction force. We have a tension. I'm calling it T2. And we have the weight of gravity, which we can split into, excuse me, mg cos theta, mg sine theta. Good? So in order for this object to accelerate up the incline, this force, T2, has to be greater than the sum of the two that are pulling it down the incline, right? So T2 has to be greater than the friction force plus the weight in that direction down the incline. So what is the person saying here? The tension in the rope has to be larger than the force the lower block exerts on the rope. So what is the tension in the rope? Is the force the rope is exerting on the lower box. And so how much force is the lower box exerting back onto the rope? These two forces have to be what? Equal in magnitude, right? Opposite in direction. So it's a Newton's pair, right? If the rope is pulling on the box with a certain force, the box is pulling back on the rope with the same force. Their person that's stating this is mixing some things up. We're okay with this one? So we understand the tensions. One has to be greater than 2. We understand what 2 has to be greater than. Tension 2 has to be greater than friction plus mg sine theta. And that these two forces are a Newton's pair. They have to be the same magnitude, opposite direction. Okay. Let's take a look at this one. We've got a massless rope connecting a box on a horizontal surface and a hanging stone. The rope passes over a massless, frictionless pulley. The box is given a quick tap, so it slides to the right along the horizontal surface. The figure below shows the block after it has been pushed while it is still moving to the right. After it's been pushed, but while it's still moving to the right. Mass of the stone is larger than the box. There is friction between the box and the horizontal surface. Free body diagrams have been drawn by a student. So we're critiquing the free body diagrams. So maybe you should draw your own free body diagrams before you look at these and see if they're the same or different. So go ahead and draw free body diagrams for the stone. And for the box. And what differences? Can you spot any problems? Let's do the stone first. Is the stone okay? The hanging object? I think the stone looks pretty good. This is how I would have drawn it. Looks about right. How about the box? Question about the stone. If it's moving up at constant velocity, shouldn't the vectors be equal lengths? If it was moving up at constant velocity, yes, the vectors should be equal lengths, but it's not, right? What's happening here? We gave it a push. We gave the box a push, quick push to the right. So at this instant, it's moving at 2 meters per second. But an instant later, how fast is it going to be moving? You've got a big stone hanging off the other end, gravity pulling on it, right? So this box is going to be slowing down. The stone is going to be slowing down. And so that's why they've got this vector is longer than this vector to show that the acceleration is in this direction, causing the stone to slow down. As it's moving up, it's slowing down. Eventually it'll come to rest, and then it'll start to slide in the other direction, right? Good. So this friction is in the wrong direction. So if I was to draw this, I would have my normal force. I would call it N. M box times G. I have a tension in this direction and friction force in this direction. And that's what it would look like. Nothing is causing the box to go to the right after it leaves your hand, after you give it the push, right? Everything is causing it to slow down. All right. Good. So we'll take a little break here, 10 minutes, and then we'll continue with Newton's laws and free body diagrams. Okay, let's do the next one. So we've got a box being pulled on a rough horizontal surface. 100 Newton box, initially at rest. Coefficient of static friction is 0.6. Coefficient of kinetic friction is 0.4. A constant 35 Newton horizontal force is applied to the box. 4 students are discussing the friction force exerted on the box by the surface 1 second after the force is first applied. Okay, you understand the situation. 100 Newton box sitting there, 35 Newton constant force being applied. 1 second later, what's the friction force? So student A says, the friction force is 60 Newton since the box will not be moving. Coefficient of static friction is 0.6, normal force of 100. Student B says the friction force is 40 Newton since the coefficient of kinetic friction is 0.4, normal force is 100. Student C says friction force is 35 since the box will not be moving, and the friction force will cancel out the applied force. Student D, it's 40 Newtons for kinetic friction. It's 60 Newtons for static friction. The normal force is 100. Coefficient of kinetic friction is 0.4, 40 Newtons for kinetic friction. Okay, there, student D sounds like they're restating a lot of stuff and not really telling us anything. So is the box going to move? It started out at rest. Is it going to move? No, because the maximum static friction force is 60 Newtons, right? So as we pull, if the box sits there at rest with no force on it, the friction force is 0. Now we pull with the force of 35 Newtons, we'll pull with the force of 5 Newtons, and the friction force is 5 Newtons. Pull with the force of 10 Newtons, and the friction force is 10 Newtons, right? It keeps increasing, and it would keep increasing up until it hit its maximum value of 60 Newtons. Static friction can hit a maximum value here of 60 Newtons. But we never get to 60 Newtons. We only get up to 35. So that's where it stops. So when we get to 35, the friction force is 35. And it stays 35 Newtons. All right. Let's take a look at this situation. We've got these boxes. And this is what I want to do. Forget the question. Ignore the question here. I'm going to give you some more information. Now, we know the weights. We know the pulling force. We know the angles. So I'm going to add in here if mu static 0.5 and mu kinetic 0.2. Number 1, Does the block begin moving? If assuming it started at rest, right? Number 2, find the friction force on the block after 1 second. And number 3, find the acceleration. Okay, so there were 2 here. I added a third one, so A, B, and C. Let's do C first. Okay, we'll do C first, and then we'll do one of the other 2, and then you can do the third one later if you need to. So we'll do C, and then we'll do A. So go ahead, set up C. Think about what you think is going to happen there. We're just doing C right now. Draw a Freebody diagram. Okay, they're telling us the weight of the box is 50 newtons. That's nice. We're pulling with a force of 40 newtons. And there's something is going to pull back on us. We don't know if it's static or kinetic, but something is going to pull back on us. Friction. So if I call this my positive X and this my positive Y, I can say the sum of the forces is MA, and we break that up usually, right? Sum of the forces, I'll call it the Y direction here, has to be what? Zero, because the box doesn't jump up off the incline, doesn't jump up off the ground or anything, right? It never moves in the Y direction. So the sum of the forces has to be 0. Why do I do the Y direction? To figure out what the normal force is, right? This gives me the normal force. So in this case, the normal force is pretty obvious, right? But in the other 2 cases, it isn't, right? The normal force for A or B is a little tricky. And so drawing out the Freebody diagram and looking at the sum of the forces in the Y direction makes sense in those cases. But I'm going to do the same process for all of them. So I've got normal force minus mg is 0. The normal force just equals the weight of the object. In this case, 50 newtons. Now I know the normal force, I can find my maximum static friction force. Okay, does it move? Yes, it moves because we are pulling with a force of 40. So the maximum static friction force is less than our pulling force. Right, 25 is less than 40. So it moves. So if it moves, what does that mean? Kinetic friction, right? You have only one kind. You either have static friction or you have kinetic friction, never both, right? The object is either, the surfaces are either stationary with respect to each other, right? Static with respect to each other, or there's sliding, kinetic. You can't have both. It's one or the other. So as soon as we know it starts to slide, we know we're kinetic friction mode. So we need to find the kinetic friction force. Mu times the normal force. What was it? It was 0.2. 10 newtons. And now we want the, so what were the questions here? Does it move? So we said, yes, this one moves. Find the friction force acting on the box. So once it starts moving, we know it's kinetic friction. That's easy to find. We did that. Now it says find the acceleration. So let's do that. Find the acceleration. And what do we have? We had our 40 Newton pulling force minus our kinetic friction force equals MA. And what is M? And M is 50 over 9.8. And so my acceleration is about 6, right? Okay, we okay with this one? We ready for a more interesting one? So go ahead, follow the same thought process and work your way through for box A. Box A is that one. The tension in the string is angled up at a 30-degree angle. or our pulling force is angled up at a 30-degree angle. Draw a free body diagram. Find your normal force. Because you need that to figure out friction. Okay, so our free body diagram should look something like this. You want to break up that pulling force, that tension in the string or whatever that is, the 40 Newton force into a horizontal and a vertical component. I'm calling it T, but I'm going to plug in 40 in there in a minute. So what do I have here? I've got some of the forces in the Y direction have to be 0. And so my normal force is 30 newtons. It's less now, right? Normal force is 30 newtons, and it's less than it was. It's less than the weight of the box because the string is holding up some of the weight of the box. The surface doesn't have to push up with as much force. We know gravity is pulling down with 50. If the string is holding part of the weight, then the surface only has to hold part of the weight, so less than 50. And if you do box B later at home, the string is pulling the box down into the ground. So not only is the surface holding up the weight of the box, it is also has to hold up part of the pulling force down. So the normal force is going to be bigger than the weight of the box. So what's my maximum static friction force now? So find 15, right? Mu and does it move? Maximum static friction force is less than the pulling force in the x direction, right? So I'm comparing Fs maximum with T cos theta, right? 40 cos 30 degrees and 15 34.6. So it moves. So if it's moving, we are in kinetic friction mode. So we can find the kinetic friction force. And then the last thing is to find the acceleration. Sum of the forces is ma. So in the positive direction, I have my T cos theta. In my negative direction, I have my friction force. And this was, I already calculated this, it was 34.6, and friction force is 6. 50 over 9.8 is the mass, and I get my acceleration is approximately 5.7. Is that right? $6.6. Okay, perfect. Okay, so there's one more here for you to do at home. Box B, but this is a good way to think about things. You know, is it going to start to move? Yes or no? If it does move, what's the friction going to be? If it doesn't move, what's the friction going to be? Things like that. All right. Application of the day. Let's do this. So a few things here. We're talking about inertia today, mostly. Figuring the weight of an object. So if I were to ask you to play along with me for a second and hold your hands out in front of you and pretend you had my cell phone in one hand and my wallet in your other hand. What could you do to tell me which one is heavier? What are you going to do to tell me which one is heavier? If I could see you right now, you know what I would see? I'd see a lot of people doing this. Why are you shaking them? Because you know about inertia. You know if you hold two objects in your hands that are about the same weight, you'll never tell them apart. But the heavier one has more inertia. It's going to resist changes in motion more. And if you shake them, you might be able to detect that. So that's the idea with inertia. Okay. Let's take a look. Getting the ketchup out of the bottle, right? That's classic. You got that last little bit of ketchup in the bottle. What do? You get the bottle moving really fast, and then you stop it. The ketchup keeps moving towards the front of the bottle until it, because it has inertia, right?
Yeah. Okay, then. Wow.
Okay. There we go. All right. I had a student a couple of years back asked me about something called, she was really into horse, I don't know what they call it, the jumping horses over these obstacles and things. And she said that sometimes the horse decides not to jump over the obstacle. It's called a refusal. And when that horse refuses to jump over, what happens to the rider? Yeah, the rider keeps going because they have inertia. And so when the horse stops, they're running up towards that jump. When the horse stops, the rider keeps going. It's the same reason you should wear your seatbelt when you're in your car, right? If the car stops suddenly, if it hits something, your body wants to keep going, and you don't want that to happen. What else we got here? Shopping cart video. Where's my video? Okay, so this is a fun. Let me share this with you. Hold on. This is a video from behind a Target store. Those shopping carts sitting in a truck. They are a relatively low friction surface. They're on wheels, right? Oh, the truck is moving. So where are those shopping carts now? Pretty much in the same place, right? Just a little lower to the ground. This is like the tablecloth demonstration you see a lot of people do, only it's kind of supersized, right? That's a fun one. And then what is the last one here? It's the reason the salsa ends up on your shirt when you're eating chips and salsa. You're wondering what I mean by that, right? Luckily, I have a video. So here's me eating chips and salsa. And I know what you do, right? You lean out a little bit like this, right? So that if the salsa falls, it doesn't land on your shirt. But what happens, right? What happens? The salsa is moving toward you, right? Where's that salsa going to go? It's not going to fall straight down. It's going to keep moving toward you because it has inertia. And where's it going to end up? Oops. It's going to end up on your shirt right there, right? Soup, salsa, same thing, right? You get it moving toward you, a little bit drips off, it doesn't go straight down, it keeps moving toward you. That's why it gets your shirt, okay? There we go. All right. So lots of examples of inertia all around us, right? Things keep moving on their own once they're moving. And we see that all around us. Okay. Let's do a couple of problems. You got an exam coming up, right? Let's do a couple of problems. Let's see. How about circular motion? Should we do circular motion, or should we do a... We'll do both. Let's do this. Let's do a pulley problem first, and then we'll do a circular motion problem. So this is, if this is not your favorite problem yet, it will be soon. We'll do 2 blocks on an incline with a pulley. Call that M1, call that M2. Oh, sorry. I've got to share this screen back. There we go. Okay, your favorite problem. Like I said, if it's not your now, it will be soon, because we're going to take the same problem in a couple of weeks. We're going to put some springs in there. And then a week or so after that, we're going to allow the pulley to have mass. And so we're just going to keep revisiting this problem over and over and make it more real world as we go. Okay, so let's, if we're given M1, M2, theta, mu, that's a mu k, find, does it start moving? From rest? And if so, find acceleration and tension. Now, in order to do this, we need some numbers, right? So let's let theta be 30 degrees, M1 20 kilograms, M2 2 kilograms, mu static 0.4, and mu kinetic 0.2. So now we've got some numbers, and we can go through and see if it starts moving, and if it does, we can solve for acceleration and tension. So I'm going to start out with my system schema. I just want to show you that everything, in this case, everything is going to be in our system. If we were using energy to solve this, we could use the entire system in our as a conserved energy problem, because nothing is reaching in. But what we have is two masses, the Earth and a rope, right? So we have M1, we have M2, we have a rope, we have an Earth. And the rope interacts with M1, that's a contact force. And the rope interacts with M2, that's a contact force. M2 is interacting with the Earth through a non-contact force, right? That's gravity. And M1 is not only touching the Earth, and how do we normally have a contact force with the Earth? We have it as a double, right? A normal force and a friction force, right? I'll put it like that. Contact force there. And then what can reach in from a distance? Gravity. So there's my system schema. Because the rope is completely in the system, I don't really worry about it, right? When I do, you'll see when I do energy problems, if the whole rope is in my system, I don't care about it, because whatever it does to one block, it does the opposite to the other one, right? If it makes one block speed up, it makes the other one slow down, right? It's the internal forces cancel out. It doesn't do anything to my system. Where I have to deal with a rope is if I only have one end of a rope in my system. Then I have one end of a rope reaching into my system doing something, and I have to account for that when I get to energy. Okay, so right now, this might help us draw our free body diagrams, but it's really most important when we get to energy. So let's draw free body diagrams for M1 and M2. I'll do the easy one for you while you're doing the hard one. M2. I have two forces acting on M2. And if I look at my system schema, what do I see? I see two forces acting on M2. And there they are. Okay, now the other one, hopefully you've got it already. I like to kind of sketch in where the incline is. Just helps me draw things. You don't have to do that if you don't need it. Normal force is perpendicular to that surface. I have a tension in the string. We've got the gravity. We can break gravity up into M1g cos theta and M1g sine theta. And then there's there's friction. And we need to figure out friction. Which way does friction go? So if we are just holding this system at rest, if we're holding it at rest, what's the tension in the string going to be initially, just as we let go of it? Let's look at this. If this isn't moving, if M2 is not moving, what's the tension in the string have to be? M2G, right? The weight of M2, it's holding up M2. If M2 is not moving, the tension in the string is M2G. If M2 is accelerating, the weight is not going to change, right? So the tension in the string has to change. If M2 is accelerating up, the tension in the string has to be greater than the weight. If M2 is accelerating down, the tension has to be less than the weight. But if we're just holding the system at rest and we're going to let go of it, that initial tension is M2G. So what did I say? That was 2. I'm going to use 10 for G. It's about 20 newtons. Now, what's pulling it? So that's what's pulling it up the incline. What's pulling it down the incline? m1g sine theta. So now we need to see what is m1g sine theta. So that's 20 times roughly 10. Sine of 30 degrees is a half. 100. Is that right? Okay. So, so what's it going to do? It's going to want to slide down the incline, right? So M1 wants to slide down the incline. So the friction force has to be up the incline. So I can come back up here now and draw in my friction force. We okay with that? I'm saying if I'm looking at the forces acting on M1, right? I know friction is acting on it somewhere, but before I figure out what direction friction is, I need to figure out what the remaining forces are trying to do to M1. So tension is trying to make M1 go up the incline. Mg sine theta is trying to make M1 go down the incline. So I want to see which one of those is bigger, which one of those is winning the tug of war here on M1. If the tension is bigger, then M1 would want to go up the incline if there wasn't friction there. So friction would have to oppose that motion, right? In this case, M1g sine theta was bigger. So in the absence of friction, the box would slide down the incline. So friction has to oppose that motion. Okay. So now we have to say to ourselves, does it slide or not? We know that friction is going to be up the incline. Maybe it's static friction is enough to hold it and it won't move. Maybe not. Maybe there's not enough static friction there and M1 will actually start to slide down the incline. So we have to find the maximum static friction force. And in order to do that, we need the normal force. We need N. So find N. Sum of the forces in the perpendicular direction. I'll use parallel and perpendicular. So let's call this my, where am I running out of room here? I'll go this way. This is going to be my parallel direction, and this is going to be my perpendicular direction. Excellent. Some people already have it. Good. So I've got normal force equals M1g cos theta. And that's going to be about 173. And so what's my maximum friction force? 0.4, 173 newtons. About 69 newtons. Okay. So now we have to ask ourselves which the forces are the forces down the incline. How do they compare to the forces up the incline? So what do we have down the incline? We have mg sine theta. And we want to know, how does that compare? That's a question mark. How does that compare to the maximum static friction force plus the tension, initial tension in the rope? So 100 is greater than 69 plus 20, 89, right? 100 is greater than 89. So it slides down the incline. That means we are in kinetic friction mode. So now we know it's kinetic friction, so we can find the acceleration and the tension. We have two masses in our system, and for each mass in our system, we can say sum of the forces equals ma, right? Newton's second law. So we get an equation for each one. So two equations, two unknowns, we can solve simultaneous equations. So let's do the easy one first, m2. And I like to pick the direction of my acceleration as my positive direction. I know M1 is going down the incline. I know my acceleration is in this direction, right? I have a net force in that direction. And so I'm going to choose that as my positive direction, and I'm going to choose this as my positive direction because I want them to be the same. When M1 goes in the positive direction, M2 should also go in the positive direction. And what do I get? Tension minus M2G is M2A. So they've got one equation here with two unknowns. So I should point out here, note, the tension does not equal M2G anymore, right? I used the tension equals M2G for the initial tension, right? Just at the instant we were letting go of it, what was the tension in the rope? But once you let go of it and this thing starts to move and accelerate, the tension in the rope cannot be equal to mg anymore, or M2 would not accelerate, right? Let's look at our Freebody diagram for M2. We've got a force up, we've got a force down. If those are equal, there can't be any acceleration, right? So once this thing starts to move, once we let go and let it move, the tension is more. The tension becomes greater than M2G, and M2 accelerates upward. Okay, Now, if we look at M1, we have sum of the forces on 1 is M1A, and we can split that up into perpendicular, and that tells us the normal force is 173 newtons. We did that already, right? And we have sum of the forces in the parallel direction is M1A. Down the incline is my positive direction. So just 2 more lines here and then I'll end it. M1G sine theta is the force in the positive direction. In the negative direction, I've got friction, I've got tension. Those add up to be M1A. And so I'd have to plug in friction. I can't leave it like that. I have to put it in terms of things I know. M1G sine theta, those are all things I know. Mu K times my normal force. I know my normal force. So there's my other equation. Now I can solve for acceleration and tension. Okay. All right, so we covered a lot today. Look over that, all those scenarios and different setups. We'll do some more with, we'll just do some review, conceptual things, and we'll do another 1 or 2 circular motion problems next time. Remember office hours, 4 to 5 o'clock, 4 to 5 every day. Don't forget about STEM Center. If you're working in the afternoon and you need some help, or at night or on the weekend, the STEM Center has pretty extended hours. So check that out. You can get help right away. And let me know. I'll stick around. I'm going to stop the recording now. I'll stick around for a few minutes. If there are questions now, we can cover them. Otherwise, I'll see you